Far beyond Pluto, beyond the Kuiper belt, and almost halfway to the nearest stars, the solar system fades into a dark sphere of frozen objects called the Oort Cloud. It looks silent, distant, and empty. In reality, it may be the source of some of the most dangerous visitors ever to enter the inner solar system. Tonight, this journey moves from that hidden frontier inward to reveal why the Oort Cloud is far more terrifying than it first appears. Please like the video and subscribe to the channel for more deep space mysteries. Far beyond the last bright orbit of the known planets, beyond the flattened belt of icy bodies that circles in the same broad plane as the worlds, there is a region where the solar system begins to lose its familiar shape. Here the sun no longer rules in any vivid or obvious way. It still holds matter with gravity, but that hold becomes thin across distances so large that the old image of a central star with planets around it no longer explains very much. The space beyond the outer edge of the Oort Cloud belongs to the wider sea between the stars. In that region, the solar system is not a compact place with a clear wall. It is a fading sphere of influence inside a much larger galactic environment. The darkness there is not empty in the simple sense. It contains gas so thin that it barely resembles anything known on Earth. It contains dust grains, magnetic fields, energetic particles, and weak radiation from many directions at once. Starlight still crosses it, but no single light dominates the view in the way the sun dominates the sky above Earth. From such distances, the sun shrinks into one bright star among many. It remains somewhat brighter than most surrounding points because it is nearby galactic standards, yet it no longer fills space with a clear sense of home. This is one reason the region feels unsettling in scientific terms. Human thought often treats the solar system as a finished structure, as if it ends where the planets end. Modern astronomy does not describe it that way. The larger system extends outward until the sun's gravity gives way to the stronger combined influence of other stars and the galaxy itself. That change does not happen at a sharp line. There is no fixed shell, no glowing marker, no natural border stone. Instead, there is a broad transition in which the sun's hold weakens and external influences matter more and more. Distance here resists instinct. Near Earth, distance can be imagined in travel time, in landscapes crossed, in horizons approached. Far beyond the outer planets, those habits fail. Astronomers often use the astronomical unit, meaning the average distance between Earth and the Sun, because ordinary measures become too cumbersome. Even this larger unit starts to feel small. The great outer reservoir associated with the Sun extends to tens of thousands of these units. Beyond that scale, the nearest stars cease to seem impossibly remote, and begin to feel like neighbouring presences in the same vast field. The nearest stellar systems are still far apart, but not far apart compared with the full breadth of the Sun's distant domain. That fact changes the meaning of outer space. It is not merely emptiness beyond the planets. It is a contested gravitational environment. Every star moves through the Milky Way while carrying its own retinue of matter and influence. The Sun does the same. As it travels around the centre of the galaxy, it passes through changing stellar neighbourhoods over immense spans of time. Some stars drift relatively near. Most remain distant enough to cause only subtle effects. Yet even distant stars contribute to the slow rearranging of the Sun's farthest surroundings. Time also changes character here. A human life is too short to witness the region in any complete way. Even a civilization would see little more than a frozen view. The important changes happen across millions of years. A star passes at a distance that still seems enormous, and yet that passage matters. The Sun moves through another part of the galaxy, and the background pull becomes slightly different, Nothing in the scene appears hurried, but the calm is deceptive. Slow influence is still influence. The Milky Way itself presses on this region in a quiet way. Its mass is spread through stars, gas, dust, and dark matter across a rotating disk and halo. That mass creates a broad gravitational field, often called the galactic tide. A tide in this sense is a gentle difference in gravitational pull across a large distance. Near Earth, tides raise and lower oceans. On the scale of the outer solar system, the same principle acts across enormous reaches of darkness. Nothing crashes, nothing flashes. The process is slow and nearly silent. Yet across millions of years it can loosen balances and make the sun's most distant holdings only partly its own. This outer region also exists beyond the heliopause, the boundary where the outward flow of charged particles from the sun gives way to the surrounding interstellar medium. That boundary is important, but it is not the true end of the solar system. Human machines have crossed into interstellar space by passing beyond the sun's particle bubble. While remaining vastly closer to the sun than the main body of the Oort cloud is thought to begin, interstellar space and the solar system overlap. The sun's wind does not define the full extent of the sun's gravitational reach. In such a place, orientation loses comfort. There is no up or down that belongs to the planets. There is no bright ring of familiar worlds to provide a frame. The broad flatness that shapes the major planetary orbits becomes less important. Motion continues everywhere, yet almost nothing seems to move in any visible human way. Stars change position only over long spans. The sun advances through the galaxy. Thin gas flows, fields shift. Gravity adds tiny changes upon tiny changes. The region appears still while remaining dynamically alive. That combination of stillness and exposure gives the outer edge of the sun's domain its cold character. It is not terrifying because it is violent in any ordinary sense. It is terrifying because it is indifferent, porous, and difficult to define. A boundary that cannot be seen is harder to trust than a boundary that can. A system that fades gradually into a larger one feels less secure than a system enclosed by a wall. From this far outside, the familiar solar system is reduced to an inner brightness, lost inside an enormous sphere of possibility. The old center still exists, but it no longer explains the whole. At its widest edge, the solar system is not sealed. It is open to the galaxy. At the outer boundary of the Oort cloud, distance stops behaving like an extension of the planetary system and starts to resemble a separate environment. This boundary is not known as a directly seen surface. It is an estimate built from orbital theory, from the motion of long-period comets, and from models of how far the sun can continue to hold small icy bodies while the galaxy and neighbouring stars keep tugging at them. Observations indicate that the cloud may extend to roughly 50,000 astronomical units from the sun, and some models allow even greater distances. At that scale, the outer edge lies a substantial fraction of the way to the nearest stars. The solar system no longer feels like a compact family of worlds. It becomes an enormous and thinning domain, whose far side approaches the shared space between stellar systems. This boundary is terrifying in a calm way because it is real in effect but unclear in shape. There is no bright wall of ice. There is no dense shell. There is no region where countless frozen objects crowd together so tightly that one could imagine a solid border. The Oort cloud is thought to be extremely sparse. Each object may be separated from the next by distances that remain immense even on the scale of the outer solar system. The boundary therefore marks not a crowded limit but the last reach of a weak organizing force. It is the point at which the sun can still keep an object in a very long orbit. but only just. Gravity at this distance still acts, yet it acts with great fragility. The Sun remains the central mass, and every distant body in the cloud is understood as belonging to it in the orbital sense. Even so, the bond is loose. A small change in motion, applied gently across enough time, can alter an orbit in a meaningful way. The farther outward one goes, the more true this becomes. Near the outer edge, the Sun does not grip matter with the firmness seen among the planets. It retains it like a fading memory. The body still circles the Sun, but it does so across an orbit so wide and slow that a full journey may take millions of years. The objects that may inhabit this outer limit are thought to be ancient icy leftovers from the early solar system. They're not active in the way inner comets later become active. At these distances, sunlight is too weak to warm their surfaces in any meaningful way. They remain frozen for spans of time that dwarf the age of human civilization. They do not shine on their own. They reflect so little light and sit so far away that present astronomy has not directly imaged the cloud itself. This means the boundary is not a line drawn from sight. It is a line inferred from the balance between what the Sun can keep and what outside forces can take. That balance is delicate because the boundary exists inside a living galaxy. The Milky Way is not a background picture. Its gravity acts across the whole solar system, and at the Oort Cloud's outer fringe that action becomes especially important. The galactic tide slowly changes distant orbits. Passing stars, even when not especially close in ordinary galactic terms, can disturb these outermost bodies. A cloud object near the Sun would barely notice such influences. An object near the cloud's outer edge may respond over time with a shifted path, a loosened orbit, or a complete departure from the Sun's domain. This gives the outer boundary an almost temporary character. It exists, but it does not exist as a permanent geometric truth. The limit changes slowly as the Sun moves through the galaxy, and as the stellar neighborhood evolves. Over vast intervals, nearby stellar passages and galactic tides may compress or stretch the effective reach of the cloud. Some bodies are likely lost, others may be nudged inward. The outer edge is not a hard shell that simply remains where it is. It is better understood as a changing frontier shaped by competing pulls. Distance there also reshapes the meaning of separation. The nearest star to the Sun lies a little more than 4 light-years away. The estimated outer edge of the Oort Cloud reaches a notable fraction of that distance. This does not mean the cloud touches another star's cloud, and it does not suggest a simple overlap. The spaces between stars remain vast. Yet it does mean that the Sun's most distant reservoir is not isolated from the broader stellar setting in any emotionally comfortable way. The outer solar system extends so far that interstellar space no longer feels truly separate from it. The border between belonging to the Sun and belonging to the galaxy becomes a matter of degree. That is part of what makes the region more frightening than it first appears. The Oort Cloud is often imagined as a remote storehouse of comets, interesting but passive. Its outer boundary shows a different truth. The storehouse sits almost unguarded at the edge of a much larger gravitational world. The Sun has carried this vast sphere through the Milky Way for billions of years, and its farthest pieces have never been fully sheltered. They exist in a zone where long silence does not equal safety. A passing star does not need to strike the cloud to matter. The galaxy does not need to erupt into violence to reshape it. Very weak forces, repeated over immense time, are enough. The boundary also forces a change in perspective about ownership. In the inner solar system, belonging is easy to imagine. Earth belongs to the Sun. Jupiter belongs to the Sun. Their motions are obvious parts of a structured system. At the outer boundary of the Oort Cloud, belonging becomes statistical and provisional. A body may still be sunbound, but only in the sense that its orbit has not yet been erased or stolen by outside influence. It remains part of the solar system, though only tenuously. The farther out the body lies, the more the word part begins to feel like an arrangement rather than a certainty. This is the last broad reach where the Sun can still claim a surrounding population of icy remnants as its own. Beyond it, the claim fades into the common medium of the galaxy. The outer boundary of the Oort Cloud therefore stands as the solar system's least visible frontier and one of its most unsettling ones. It is not dramatic in appearance. It is dramatic in implication. It reveals that the Sun's true domain is vastly larger than the planetary region, yet also far less secure. Its greatest extent is also its weakest, and its farthest border is where the solar system becomes hardest to distinguish from everything beyond it. The outermost reaches of the Oort Cloud are not frightening because they are crowded or violent. They are frightening because they are almost impossible to picture correctly. Human imagination often fills distant places with structure. It expects an edge, a belt, a shining haze, or some recognizable pattern against the dark. This region offers almost none of that. It is thought to consist of icy bodies separated by vast intervals, each one moving through darkness so complete and so prolonged that the place scarcely resembles an environment at all. It is a frontier made not of walls or storms, but of distance, cold, and uncertainty. Here the Sun is still the centre in the mathematical sense, yet it no longer feels central in any visual sense. Its light continues to travel outward, but at this range the energy carried by that light is feeble. Illumination does not disappear, but it thins to the point that it can no longer warm surfaces in a meaningful way. The bodies thought to occupy this region remain frozen through spans of time longer than the history of complex life on Earth. Their surfaces are not softened by seasons. They are not shaped by rainfall, flowing water, or thick atmospheres. They remain in a state of deep preservation, altered mainly by impacts, radiation, and the slow chemistry of exposure in space. Cold in this region is not merely the absence of comfort. It is a scientific condition that controls everything. Ice does not behave as it does near the Sun. Volatile materials, meaning substances that easily turn from solid to gas when warmed, can remain locked in place for immense periods. Water ice may be present, but so may carbon monoxide, carbon dioxide, methane, ammonia, and other frozen compounds associated with cometary material. In the outermost cloud, these materials stay inert for ages because the sunlight is too weak to drive change. A body can remain dark, hard, and nearly unchanged while completing an orbit so long that entire species rise and vanish elsewhere before it finishes one circuit. The darkness there also has a special quality. It is not the darkness of a sealed room or a cloudy night. It is a darkness crossed by distant stars, by the faint combined glow of the Milky Way, and by the small unresolved brightness of the Sun far away. Yet none of this creates a landscape. There is no horizon. There are no nearby reference points. One icy body and the next may be separated by distances that, in the inner solar system, would contain entire planetary systems of ordinary scale. The result is a region that is populated in theory but almost empty in practice. It is less like a field of objects and more like an enormous volume in which a few frozen remnants happen to be scattered. That sparsity matters because it changes what the word cloud means. In ordinary language, a cloud suggests density, softness, and visible shape. The Oort cloud is called a cloud because it describes a broad distribution of material, not because it resembles mist. The outermost reaches are especially deceptive in this respect. There is no pale veil surrounding the sun that could be seen from a distance. There is no bright border marking where the solar system becomes something else. There is only the idea of many ancient objects occupying a gigantic region so thinly that present astronomy has not directly seen the cloud itself. This is one of the most unsettling truths about the Oort cloud. It is accepted not because telescopes have revealed a glowing shell at the edge of the sun's domain, but because the behavior of long-period comets points toward a remote reservoir. The cloud is inferred. Its general existence fits the evidence well, but its details remain uncertain. The exact number of bodies, the precise distribution of their orbits, the extent of the outermost fringe, and the full history of how that fringe changes over time are not all known with certainty. Observations indicate a vast distant source of comets. It remains uncertain exactly how its farthest population is arranged. This uncertainty does not weaken the region's reality, it deepens it. The outermost Oort cloud exists as a scientifically serious answer to an observed pattern, yet it remains hidden from direct view. That means the frontier is known first through effect, and only second through imagination. Comets arrive. Their paths imply origins far beyond the planets. Models of solar system formation and galactic influence show how such a distant storehouse can arise. Together these strands make the unseen region persuasive. Still, the place remains beyond ordinary sight, and that invisibility leaves room for the mind to feel the full scale of what is being described. The bodies in this deepest frontier are likely ancient. Many may preserve matter from the early history of the solar system, material that formed close to the young giant planets before being scattered outward long ago. If so, the outermost cloud serves as a frozen archive. Yet archive suggests order, and this place has almost none in the human sense. It keeps its records by not changing them much. It stores them in darkness, at immense range, in orbits so drawn out that stillness becomes the dominant impression. Preservation there does not feel protective. It feels remote and indifferent. The silence of the region is also scientific rather than poetic. There is little to make an object active. There is little to make it visible. Even collisions may be infrequent because the bodies are so widely spaced. One object may drift for millions of years without meaningful disturbance, then respond at last to a slow external influence, too weak to notice over a short span. The frontier is quiet, but it is not secure. It is stable only in the patient way of very distant things. What makes the outermost Oort cloud terrifying, then, is not what it does from moment to moment. It is what it represents. It shows that the solar system possesses a frozen outskirts so vast and so dim that it remains mostly theoretical in direct visual terms, yet substantial enough to send comets inward across time. It contains matter that may have waited unchanged since the youth of the sun. It occupies a region where light barely matters, where separation is immense, and where a named part of the solar system can still remain largely unseen. This deepest frozen frontier is real enough to influence the inner system, but remote enough to stay hidden in darkness, and that combination gives it its calm and lasting unease. The main body of the Oort cloud is often described as a sphere, or more carefully as a broad spherical shell surrounding the sun on all sides. This image matters because it breaks with the ordinary pattern of the solar system. The planets circle in a flattened arrangement. Most familiar small bodies also tend to follow that general plane. Their motions preserve the memory of the rotating disk from which the Sun and planets form. The main reservoir of the Oort Cloud does not preserve that shape in the same way. At this depth of the Sun's distant domain, the outer structure is no longer a disk-like family of paths gathered into one broad layer. It becomes a volume. That change in shape is one of the cloud's strangest features. Human understanding of the solar system often begins with flatness. Drawings show rings, orbital tracks, and layered belts lying around a bright center. This makes sense in the inner regions, where the shared plane of planetary motion provides a clear organizing pattern. The main Oort reservoir does not appear to obey that visual instinct. If it exists as astronomers describe it, then the Sun sits not inside a distant ring, but inside a nearly all-encompassing shell of scattered icy remnants. The cloud is not simply far away, it is far away in every direction. This does not mean the shell is smooth or exact. The word spherical is useful, but it does not imply perfection. The cloud is thought to be a thick distribution rather than a clean surface. Some regions may hold more objects than others. Some orbits may reach farther than average. Some parts may be more easily disturbed by galactic tides or passing stars. Even so, the overall concept remains important. The main Oort reservoir is understood as roughly surrounding the Sun rather than encircling it in one preferred band. Its basic geometry is three-dimensional in the fullest sense. That three-dimensional character gives the region a distinct emotional weight. A belt leaves open space above and below. A shell removes that relief. It encloses without becoming solid. It creates the sense that the Sun and planets exist inside a huge and dim surrounding population, one that extends over the entire sky if it could somehow be seen. Yet it cannot be seen that way. The shell remains too sparse and too dark. The mind must therefore hold two ideas at once. The cloud is almost everywhere around the solar system, and it is almost nowhere in terms of visible presence. This is one reason it feels more unsettling than a simple outer belt. It surrounds while remaining hidden. The shape also changes the meaning of outer and inner. In a flat system, outer often means farther along the same broad plane. In the main Oort reservoir, outer means farther from the Sun regardless of direction. There is no privileged up or down, no permanent ceiling, no permanent floor. The Sun is central not because it lights a stage with organized layers around it, but because the shell is arranged at immense range about the Sun's gravity. The familiar layout of worlds becomes only a compact interior feature. Around that compact inner structure lies a deep spherical domain that belongs to the solar system in a looser but much larger way. This geometry emerges from the history of disturbance as much as from the history of formation. Small icy bodies are thought to begin in a much more orderly setting, closer to the young giant planets, and more closely tied to the original flat disk. Over very long time, repeated gravitational scattering by large planets sends many of them outward. That process alone stretches and distorts their orbits. Then the broader environment of the galaxy, along with the influence of passing stars, slowly alters the tilt and orientation of those paths. The result is that the old flatness becomes less dominant. The distant population no longer remains confined to a common plane. Its paths fill a far larger range of directions until the cloud as a whole takes on a nearly spherical form. This does not happen in a hurried way. The transition belongs to deep time. The main reservoir therefore carries the memory of many weak changes rather than one dramatic event. A body is scattered outward. Its orbit grows huge. Long afterward, the galaxy gently adjusts that orbit again. A passing star adds another subtle shift. across immense ages, enough such changes accumulate to produce a surrounding shell instead of a preserved disk. The cloud's roundness is therefore not a simple birth shape. It is a matured shape, formed by time, distance, and exposure. Because the shell is so broad, its thickness is part of the meaning. It is not a hollow bubble with a narrow skin. It is better understood as an immense zone where many long orbits occupy a wide span of distances. The Sun lies deep inside this surrounding region, while the planets occupy only a tiny central volume by comparison. If the main reservoir could be made visible all at once, it would not resemble a fine outline around the solar system. It would resemble a colossal and very diffuse envelope, with the inner planetary system lost near the center like a grain in a vast sphere. The word reservoir is useful here because it emphasizes storage rather than activity. The main shell is not constantly producing spectacle. It holds material. It preserves it in cold orbits that may remain undisturbed for very long periods. Yet the shape of that storage matters. A spherical reservoir does not gather its contents into one route or corridor. It keeps them distributed around the Sun as a total environment. That is scientifically important because it shows how far the solar system departs from the ordinary image of nested planetary tracks. It is also quietly disturbing because it means the Sun lives inside a hidden outer population instead of merely shining outward into emptiness. The main Oort reservoir is therefore not just remote, it is enclosing. It replaces the flat architecture of the visible solar system with a much greater geometry, one built from distance in all directions. It remains sparse, dark, and largely unseen, but its form changes the entire scale of the Sun's domain. The familiar planetary plane becomes a local inner feature. Beyond it lies a spherical shell of ancient icy remnants, a vast surrounding structure that gives the solar system depth far beyond what the bright worlds alone suggest. Within the main body of the Oort Cloud, the shape of the whole reservoir becomes visible through the directions of its orbits. This is not a place where most objects move together in one broad flat sheet. It is a place where paths are tilted, twisted, and oriented across the sky in nearly every possible way. One body may travel on an orbit that carries it far above the planetary plane. Another may follow a path equally far below it. A third may move at a steep angle that cuts through the inner pattern of the solar system, as though the old flat arrangement no longer sets the rules. The cloud's surrounding geometry expresses itself through this freedom of direction. This freedom is one of the strongest clues that the distant reservoir differs fundamentally from the region of planets. The planets circle in the same general direction and remain close to a common plane because they form from a rotating disk of gas and dust. Many small bodies near them preserve that same origin. Their motions are not identical, but the family resemblance is clear. In the Oort Cloud, that resemblance weakens almost to disappearance. The most distant cometary bodies are understood to occupy orbits that can be inclined at nearly any angle. They are still sun-bound, still part of the solar system in the orbital sense, yet their motions no longer display the strong flat preference that defines the inner architecture. This gives the cloud an unusual calm disorder. The orbits are not random in the sense of lawlessness. Each one remains governed by gravity. Each follows a definite path shaped by the Sun and altered by long exposure to the wider galaxy. But taken together, the collection no longer forms a neat visual pattern. The cloud does not resemble a wheel turning around a hub. It resembles a surrounding volume filled with extremely long paths aimed in many directions at once. The result is orderly motion without a simple common plane. That broad spread of orbital tilts explains a striking fact about long-period comets. When such comets are observed entering the inner solar system, they can appear from almost any direction in the sky. They do not arrive only along the band where the planets are found. They do not announce a single lane of approach. Some descend from high northern directions relative to the planetary plane. Others rise from far southern directions. Some enter on steep slants that make the inner solar system seem open from every side. This pattern is one of the classic reasons astronomers infer a roughly spherical distant source. A flat reservoir would not send inward visitors with such a broad range of incoming directions. The unsettling character of this arrangement lies in its completeness. In the inner system, much of what moves does so within a familiar corridor. The major worlds keep to a known region of the sky. Even when small bodies wander, the old flattened origin still offers some sense of structure. The Oort Cloud removes that comfort. Its orbit distribution suggests that the solar system is not protected by emptiness above and below its planetary plane. Instead, it is embedded in a hidden three-dimensional storehouse whose members can, under the right conditions, begin inward journeys from almost anywhere around it. These orbits are also immense. Their lengths are so great that their shapes matter as much as their directions. Many are thought to be highly elongated, meaning that a body may spend nearly all of its time at tremendous distance, and only a tiny fraction of its orbital life closer to the Sun. Near the far end of such an orbit, motion slows. The body lingers in the deep cold, barely changing its position over intervals that seem long in human terms. Then, if the orbit carries it inward, it falls sunward much more rapidly. The shape of the path and the freedom of its tilt together create a reservoir that is both quiet in storage and unpredictable in how its members later appear. This orbital variety is not merely a detail of geometry, it is a record of the cloud's history. Bodies thought to have formed closer to the young giant planets begin with stronger ties to the original flat disk. To reach the Oort Cloud, they are scattered outward by planetary encounters. That process greatly enlarges their paths. Over time, the tidal pull of the Milky Way and the weak gravitational nudges of passing stars change the orientation of those paths. Their inclinations grow more diverse. Their lines of motion drift. After immense spans, the old memory of the flat disk survives much less strongly in the distant population. The cloud's broad spread of directions is therefore the signature of long reshaping by both the solar system and the galaxy. Because these changes are gradual, the region still feels still. Nothing in the cloud resembles a crowded traffic pattern. The objects remain separated by enormous distances. One orbit may cross the abstract space of another without any realistic closeness between the bodies themselves. The sense of motion comes from theory rather than sight. Yet the implications are powerful. A surrounding shell of ancient objects, moving on steeply varied paths, means that the solar system contains a hidden archive whose geometry is open in all directions. The inner planets live inside that geometry without directly seeing it. There's also a scientific humility in this picture. The exact orbital distribution of the Oort Cloud is not directly mapped in the way the planets are mapped. The cloud remains inferred, and the details of its population remain uncertain. Observations indicate that a distant comet reservoir exists, and that its source region must allow arrivals from a wide range of directions. It remains uncertain how smoothly spherical the real distribution is, how much it varies with distance, and how its structure changes across very long intervals. Even so, the directional evidence from long-period comets strongly supports a distant source that is not confined to the planetary plane. This is why the cloud's orbits feel more disturbing than a simple distant belt would feel. A belt is local in shape. It has an above and a below, It implies lanes and limits. The Oort Cloud, through the freedom of its orbital directions, implies a hidden surrounding domain instead. Its members do not merely circle far away. They inhabit a broad three-dimensional reservoir whose tilted paths transform the meaning of outer space around the Sun. The inner solar system is not bordered only at its edges. It is enclosed at every angle by a distant population of icy remnants, each moving on a path that testifies to the long and quiet work of gravity across the whole sky. The Oort Cloud is unusual among major structures of the solar system because it is accepted more from evidence than from sight. The planets can be tracked, many moons can be photographed, asteroids and nearer comet populations can be surveyed directly, even when individual objects are faint. The Oort Cloud remains different. No telescope has yet produced a direct image of the cloud as a whole, and no mission has travelled anywhere near its main body. Its existence is inferred, meaning that astronomers arrive at it through the behaviour of other things. In this case, the most important clues come from long-period comets, the rare visitors whose paths suggest that they begin their journeys at immense distances from the Sun. A long-period comet is a comet that takes more than 200 years to complete one orbit around the Sun. Many take far longer than that. Some return only after thousands or even millions of years. When such comets enter the inner solar system, they do not behave like ordinary members of the planetary family. Their orbits are extremely elongated. They appear from many directions across the sky. Some arrive on paths that seem almost new, as though the Sun has barely pulled them inward before. This pattern calls for an explanation. The inner solar system does not provide one. A distant reservoir does. The need for that reservoir becomes clear when astronomers study the orbits of incoming long-period comets. Their paths point back toward origins far beyond the planets and beyond the Kuiper belt. Many appear to have started from a region where the Sun's gravity still holds them, but only weakly. Their motion suggests a source population scattered around the solar system in 3 dimensions rather than confined to the flat planetary plane. Over time, this evidence accumulates into a coherent picture. The cloud itself is unseen, but its returning messengers leave tracks that can be measured. This is the heart of the argument. The Oort Cloud is not proposed because astronomers prefer a dramatic idea. It is proposed because the observed comets require a distant source that matches their orbital properties. Without such a source, the repeated arrival of long-period comets becomes much harder to explain. Their directions, their great orbital lengths, and the apparent freshness of some of their paths all indicate a storage region far from the Sun. The unseen cloud becomes the best fit between theory and observation. The history of this reasoning carries its own calm precision. In the middle of the 20th century, the Dutch astronomer Jan Oort examined comet orbits and noticed that many long-period comets seem to arrive from a very distant zone. Their original paths, when calculated before the planets could alter them strongly, often suggested enormous semi-major axes. The semi-major axis is the long measure of an orbit, a way of describing its overall size. These values implied source distances far beyond the known planets. Oort proposed that the Sun is surrounded by a vast comet reservoir. The idea was not a guess made in darkness. It was an answer shaped by orbital evidence. Since then, the basic picture has remained persuasive even as details continue to be refined. Astronomers improve comet catalogues, refine orbit calculations, and model how galactic tides and passing stars can disturb distant icy bodies and send some inward. The more these pieces are studied, the more the Oort Cloud remains a strong explanation. The evidence is indirect, but it is not weak. Science often works this way. Many real things are accepted before they are seen directly, provided their effects are consistent, measurable, and better explained by one model than by the alternatives. Still, the lack of direct observation matters. It places the Oort cloud in a scientifically humble category. Its general existence is widely accepted, but many details remain uncertain because the cloud itself stays beyond direct survey. Astronomers do not yet possess a complete census of its members. They do not know exactly how many bodies it contains, how the number changes with size, or how sharply one region gives way to another. They infer these things from models and from the comets that reach the inner system. Observations indicate a remote reservoir of icy bodies. It remains uncertain in detail how that reservoir is populated. The reason for this invisibility is simple and severe. The objects are small, dark, cold, and extraordinarily far away. They reflect very little sunlight. They emit almost no detectable heat. They are spread across a huge volume rather than gathered into a bright belt. Even if countless bodies occupy the cloud, each one is separated from the next by immense distances, and each one is faint beyond ordinary reach. The cloud therefore defeats direct sight not because it is imaginary, but because it is sparse and remote on a scale that current observing methods struggle to overcome. This creates a strange balance between certainty and uncertainty. The cloud is one of the solar system's most accepted unseen structures. Its presence is strongly supported by the orbital evidence of long-period comets. At the same time, its hidden nature leaves open questions about its exact extent and internal distribution. The evidence is strong enough to treat the cloud as real in the scientific sense, yet incomplete enough that the full map remains absent. There is something quietly unsettling in that state. The solar system contains a vast region believed to hold ancient icy bodies in huge numbers. Yet the structure is known mainly through the rare moments when one of its members leaves storage and falls inward. Most of the cloud remains silent. Most of its population, if the models are correct, has never been seen at all. Knowledge comes from arrivals, from paths, from calculations made after the fact. The cloud does not present itself openly. It announces itself through visitors. That is why the evidence for the Oort cloud feels both careful and eerie. The case depends on repeated signs rather than a direct view. Long-period comets appear. Their orbits are measured. Their distant origins are reconstructed. Those reconstructions point again and again toward a vast outer reservoir surrounding the Sun. The cloud itself stays hidden in darkness, but its gravitational signature reaches inward through these returning bodies. Science accepts it as the most coherent explanation for what the comets reveal. It is a place known by consequence, a region established by motion rather than sight, and that makes it one of the most persuasive invisible structures in the solar system. The bodies held in the Oort cloud are small in size when compared with planets, yet they give the region its entire meaning. Without them, the cloud would be only an abstract volume of distant space. With them, it becomes a storage place of ancient matter, a hidden population of icy remnants kept at the edge of the Sun's domain. These objects are not arranged in a way that invites easy mental pictures. They do not form a glowing band. They do not gather into a visible swarm. They remain scattered through a vast spherical region, each one dark, cold, and quiet, taken together. However, they represent one of the largest known populations of primitive bodies associated with the solar system. Astronomers generally describe these members as cometary nuclei or comet-like bodies. A nucleus is the solid central body of a comet. the part made of ice, dust, and rocky material before sunlight begins to awaken it. In the Oort Cloud, these bodies remain nuclei almost all the time. They do not display bright tails. They do not build wide clouds of gas around themselves. At their great distances from the Sun, they stay in storage. They are comets in potential rather than in appearance. Most of their existence passes in silence and darkness, without the activity that later makes some of them visible in the inner solar system. Their composition is thought to preserve material from the early history of the solar system. They likely contain mixtures of water ice and more volatile ices, along with dust, carbon-rich compounds, and mineral grains. Volatile in this context means a substance that can turn to gas when heated by stronger sunlight. In the Oort Cloud, such substances remain frozen. This makes the bodies scientifically valuable, because they are not exposed to the same long period of warming that changes many inner solar system surfaces. They serve as deep cold archives of matter that has remained largely unaltered for immense stretches of time. This does not mean they are perfectly unchanged. Even in remote storage, space continues to act upon them. Energetic particles move through the galaxy. Radiation slowly alters surface chemistry. Micrometer-scale dust and tiny impacts may mark exposed layers. Over millions and billions of years, the outermost skin of an Oort Cloud body may darken or become chemically processed in subtle ways. Yet beneath that weathered exterior, the interior may still preserve very old material in a comparatively primitive state. The cloud therefore holds bodies that are both ancient and slowly altered, preserved in bulk while modified on the surface. Their sizes likely vary. Some may be only a few kilometers across. Others may be much larger. Exact numbers remain uncertain because the cloud has not been directly surveyed, but the population is believed to span a wide range of sizes. Smaller bodies are likely more numerous, while larger bodies are rarer. This pattern is common in populations shaped by early accretion and later collisions. Even so, the lack of direct observation means the full-size distribution remains uncertain. Observations indicate an enormous distant reservoir of icy bodies. It remains uncertain exactly how many occupy each size range. The total number of members is often described in the hundreds of billions or even more, depending on the size threshold being considered and the model being used. This makes the cloud difficult to compare with more familiar structures. A population can be enormous in number, while still appearing almost empty if it is distributed through a sufficiently great volume. That is the case here. The Oort Cloud may contain an extraordinary quantity of individual bodies, yet each one is isolated by enormous distances from its neighbours. The scale of the reservoir overwhelms the scale of the members. The result is abundance without crowding. These bodies are also fragile in an important way. Many cometary nuclei studied more closely in the inner solar system appear to be low-density mixtures rather than compact solid rock. Low density means that the material is relatively porous, with empty spaces inside and a loosely consolidated internal structure. If the Oort Cloud bodies share this general character, then many of them are not hard frozen stones in the ordinary sense. They are more like fragile assemblies of ice, dust, and small grains held together by weak gravity and material cohesion. Their strength may be modest. Their survival depends less on toughness than on the deep calm of their environment. Colour likely tells part of their story as well. Bodies rich in organic compounds and altered by radiation can develop very dark surfaces. Reflecting little light, some may also take on a reddish cast, as happens with other distant icy bodies exposed to long-term space weathering. Such surfaces absorb more sunlight than brighter ice would, but in the Oort cloud the sunlight remains so faint that this does not transform the bodies into active objects. It simply makes them darker and harder to detect. Their appearance, if seen up close, may be muted rather than brilliant, more like blackened frost-covered stone than sparkling ice. The Oort cloud's bodies are terrifying in a quiet way because of what they represent. They are survivors from an early epoch, carried outward and then preserved in remote storage for spans of time that dwarf almost every familiar measure. Each one may hold chemical clues to conditions present during the formation of the planets. Each one may preserve matter older than Earth in any habitable sense. Yet they do not announce this significance. They remain lost in darkness, too small and too faint for easy detection, important mainly because they exist at all. The region therefore becomes an archive without labels. The bodies in storage are ancient, but not organized for reading. They are numerous, but not visible as a group. They are potentially informative, but usually inaccessible. The cloud keeps its records in the form of icy remnants left in cold suspension around the sun. Most stay forever beyond direct contact. A few, across immense intervals, leave storage and move inward, carrying part of that archive into regions where telescopes can finally study them. But within the cloud itself they remain what they have long been: dormant nuclei, primitive bodies, frozen members of a hidden population. Seen this way, the Oort cloud is not terrifying because its bodies are large or violent. It is terrifying because it stores so much ancient material so far from view. It surrounds the solar system with countless dark remnants of early history, each one small, cold, and mostly unseen. The cloud scale turns these modest bodies into a vast surrounding presence. Their number suggests immensity. Their isolation suggests silence. Their preservation suggests age beyond ordinary thought. Together they make the cloud feel less like an empty frontier and more like a hidden archive of ancient matter held in deep and patient storage around the sun. The Oort cloud does not begin as a distant cloud. It begins much closer to the young sun, in the broad region where the giant planets are forming, and where leftover building material still moves through the outer protoplanetary disk. A protoplanetary disk is the rotating disk of gas and dust from which planets arise. In its early stages, the solar system is not yet a settled arrangement of clear orbits. It is a crowded and changing place filled with collisions, mergers, and near misses. Within that environment, countless small icy bodies form beyond the warmer inner regions, where water and other volatile substances can remain solid. These bodies are the raw population from which much of the future Oort cloud is thought to come. At first, these small bodies belong to the same general flattened structure as the young planets. Their orbits reflect the disk in which they form. They circle the sun in roughly the same broad plane, and their motions are comparatively orderly when viewed against what comes later. They are not born in a spherical shell. They are born in a rotating system with direction and memory. This matters because it means the distant reservoir is not a primitive outer layer placed around the sun from the beginning. It is a later outcome of rearrangement. The cloud is made through exile. The most important agents in that exile are the giant planets, especially Jupiter and Saturn, with Uranus and Neptune also contributing to the long sorting of the outer system. As these large worlds grow, their gravity strengthens and begins to dominate their surroundings. A small, icy body that passes near one of them can have its orbit change drastically. Such an encounter does not need to be a collision. It is enough for the body to enter the planet's gravitational reach. the planet can then scatter it, meaning that it redirects the body onto a new path with very different size and shape. In the early solar system, when many leftover planetesimals are present, such scattering happens again and again. A planetesimal is a small body formed during planet building, larger than dust grains and capable of further growth or disruption. In the outer regions of the young solar system, many icy planetesimals remain after the main planets take shape. Some are swallowed by planets, some collide with one another, some are broken apart. Others survive repeated close passages and are flung onto larger and more elongated orbits. Each scattering event changes the balance between the body and the sun. The orbit stretches, the body travels farther outward, its return becomes slower and more uncertain. Most of these outward-thrown objects do not settle immediately into anything like the mature Oort Cloud. Many remain in unstable intermediate states. Some are lost from the solar system entirely if a planetary encounter gives them enough energy to escape the sun's gravity. Others continue to cross the domains of the giant planets and face further scattering. The process is therefore selective as well as expansive. The young solar system throws enormous numbers of bodies outward, but only a fraction end up stored in the distant reservoir. The cloud is not made by simple displacement, it is made by repeated gravitational filtering. This filtering takes time. A body may be scattered outward by one planet, then modified again on later passages. Its orbit may grow to extraordinary size while still remaining vulnerable. What matters for eventual storage is that the orbit becomes large enough, and the timing becomes favorable enough, that the body is lifted out of the strongest direct control of the giant planets before it is lost. Once the path extends to great distance, the wider galactic environment begins to play a more constructive role. The same weak external influences that later keep the outer reservoir dynamic also help create it in the first place by changing the direction and shape of these far-flung orbits. As the orbit expands, the body spends more time far from the sun and less time plunging through the planetary zone. There, distant gravitational effects from the Milky Way and from passing stars can slowly raise the closest point of the orbit. The closest point is the part of the path nearest the sun. If that point remains too near the giant planets, the body is likely to suffer further strong scattering and possible ejection. If outside influences lift that point far enough away, the body becomes insulated from repeated planetary encounters. In this way, a once unstable migrant can be parked in deep storage. It is still sunbound, but it no longer crosses the region where the giant planets can easily expel it. This is the central formation idea. The Oort Cloud is built from bodies that form nearer the sun than the cloud itself, are thrown outward by giant planets, and are then stabilized at vast distance by the broader gravitational environment. The cloud is therefore both a planetary and galactic product. The planets supply the outward scattering. The galaxy helps convert some of those stretched orbits into long-term storage. Neither part alone explains the full reservoir as well as both together do. The process also helps explain the cloud's broad three-dimensional form. The original disk provides a flat starting point, but the later distant influences gradually erase much of that flatness. As orbits are lifted, tilted, and redistributed over immense spans of time, the population becomes less like a disk and more like a surrounding shell. This transformation is not sudden. It emerges from the accumulated effect of many weak changes acting on bodies already cast outward by the giant planets. The mature cloud therefore carries the memory of both order and disruption. It begins in a disk and ends in a sphere-like reservoir. There is quiet severity to this origin story. The cloud is not a place where matter peacefully gathers. It is a place where matter is removed from the main building zone and preserved only after surviving a long sequence of gravitational dangers. Bodies that enter it are often the survivors of a violent sorting process from the solar system's youth. They are the remnants not incorporated into planets, not destroyed in collisions, and not ejected into interstellar space. Their presence in the cloud is evidence of what the young solar system fails to keep near at hand. This makes the Oort Cloud a record of early instability rather than late calm alone. Its icy members are ancient, but their storage is the outcome of upheaval. The giant planets do not merely sit in their finished orbits while a distant cloud waits around them. They help create that cloud by flinging leftover material outward on enormous paths. The broad galactic setting then helps rescue some of those bodies from complete loss and turns exile into residence. The distant reservoir is therefore built through scattering, survival, and storage. It is not the untouched edge of the solar system. It is one of the clearest signs that the solar system once throws part of its own early substance to the farthest limits of the sun's reach. The Oort Cloud does not remain still simply because it appears still. Its great distance from the sun makes it vulnerable to forces that should matter little closer in. In the inner solar system, the sun's gravity dominates so strongly that outside influences are usually negligible for the long-term paths of planets. In the Oort Cloud, especially across its broad outer reaches, that dominance weakens. A body there still belongs to the sun in the orbital sense, but only loosely. This means that even very gentle external forces can shape its path over immense spans of time. The cloud is not only a storage region, it is also a region of slow disturbance. One of the most important of these disturbances comes from the Milky Way itself. The sun does not sit motionless in empty space. It travels around the centre of the galaxy, embedded in a much larger gravitational field created by stars, gas, dust, and dark matter. That broad field does not tug equally on every part of the solar system. The difference in pull from one side of a very large system to the other is called a tide. In Earth's oceans, tides are familiar as rising and falling water caused mainly by the moon and the sun. In the Oort Cloud, the galactic tide works on a vastly larger scale and through a much weaker, slower, but persistent difference in gravitational pull. This tide does not rip through the cloud like a wave. It acts by patient distortion. A distant icy body follows its immense orbit around the sun, yet at the same time it feels the larger background of the galaxy. Over a short interval, the effect is tiny. Over millions of years, the effect accumulates. The shape of the orbit can change. Its orientation can drift. Its closest and farthest distances from the sun can be altered. A body that once seemed securely stored may slowly find its path adjusted by the combined gravity of the Milky Way. Nothing in this process is sudden. Its power comes from duration. The direction of the galactic tide matters as well. The sun moves within the galactic disk, and the gravitational environment is not identical in every direction. The result is that distant orbits do not remain locked in their original arrangement. The tide tends to be especially effective at changing the angular structure of the most weakly bound bodies, those whose orbits extend farthest and whose attachment to the sun is most fragile. In this way, the galaxy acts not as a violent intruder, but as a continuous shaping presence. The Oort Cloud exists inside the solar system, yet it is never isolated from the larger system that contains the sun itself. Passing stars provide another important influence. The nearest stars are still very far away in ordinary terms, but at the scale of the Oort Cloud, stellar passage becomes meaningful. A star does not need to plunge through the cloud to matter. It only needs to pass near enough, and slowly enough, for its gravity to add a measurable disturbance. Such encounters are rare on human timescales, but normal on galactic timescales. Over the age of the solar system, many stars are expected to pass within distances that can alter the orbits of the Sun's most distant icy bodies. These stellar disturbances vary. Some may be weak and affect only the farthest fringe. Others may be stronger, especially if the passing star is relatively massive or moves nearby at a favourable speed and direction. In each case, the change arises from gravity alone. The cloud object remains extremely far from the intruding star, yet because it is already so loosely held by the Sun, even a modest gravitational nudge can matter. An orbit may be tilted, stretched, compressed, or shifted in its orientation. A body may become more tightly bound to the Sun or less so. In some cases, it may be removed from the solar system entirely. This vulnerability makes the Oort cloud feel less like a sealed archive and more like a borderland. Its members are ancient, but their storage is never perfectly secure. The farther out one goes, the less permanent any given orbit becomes. A body may circle the Sun for immense intervals, only to have its path altered by a stellar passage that occurs once in many millions of years. The change may still be small by ordinary standards, yet large enough to transform the body's long-term future. This is a region where great distances produce great sensitivity. The combined effect of galactic tides and passing stars also helps explain why the cloud remains an active source region over deep time rather than a static fossil. If the distant reservoir were perfectly isolated, its population would simply continue on the same paths indefinitely, unless disturbed from within. But the Oort cloud is not isolated. The galaxy slowly works upon it. The Sun carries it through changing neighbourhoods. Other stars come and go. These influences continually reshape the cloud's outer architecture. Some bodies are gently loosened. Some are nudged into new orbital states. Some are lost to interstellar space. The reservoir persists, but it persists in motion. This motion is still calm in appearance. The cloud does not shimmer or churn. No eye could watch the process unfold. The timescales are too long and the distances too vast. Yet the scientific picture is dynamic. A distant object may spend millions of years in an orbit that appears stable, only for the background structure of the galaxy to work upon it so gradually that its path becomes noticeably different only when compared across enormous spans of time. Stability in the Oort cloud is therefore often provisional rather than absolute. What seems frozen is only slowly changing. There may also be disturbances from more diffuse structures, such as giant interstellar clouds of gas, though their importance relative to stars and galactic tides depends on the encounter and the model used. The central point remains the same. The Oort cloud is exposed. Its great extent places it in a realm where the Sun's gravity must share authority with the broader galactic environment. That exposure is one reason the cloud becomes such an enduring source of cometary bodies. It is not simply a warehouse at the edge of the solar system. It is a warehouse with doors that never fully close. This is why the forces acting on the cloud feel so unsettling. They're weak enough to be almost invisible in principle, yet strong enough to matter profoundly over deep time. A passing star far beyond the planets, a galactic tide too gentle to notice over a lifetime, a broad background pull from the Milky Way itself. None of these seems dramatic in isolation. Together they keep the distant reservoir from ever being perfectly at rest. The Oort Cloud lives under the influence of immense but quiet powers, and those powers reshape it with patience rather than violence. In that patience lies much of its unease. It is a realm where almost nothing happens quickly, yet almost nothing remains untouched forever. The first inward fall begins almost invisibly. Nothing in the distant Oort Cloud resembles a launch. There is no explosive release, no sudden burst of light, no clear dividing moment that announces departure to any watching eye. A body remains what it has long been, an ancient frozen remnant moving in a huge sun-bound orbit through deep cold and darkness. Yet over immense spans of time, the orbit itself changes. A gentle disturbance from the galaxy or from a passing star alters the balance just enough that the object is no longer held in quiet storage alone. Its path begins to aim inward. This change is usually best understood through the closest point of the orbit to the Sun. For a body resting in very distant storage, that closest point may still remain far beyond the known planets. Even during the inward part of its orbit, it may never come near the inner solar system unless something reshapes that geometry. The crucial step is therefore not simply that the body exists in a long orbit. The crucial step is that its orbit is adjusted so the nearest part of the path lies meaningfully closer to the Sun than before. A distant remnant becomes a future visitor only when that threshold is crossed. The adjustment can be small in immediate terms and enormous in consequence. A weak gravitational nudge does not need to throw the object violently inward. It only needs to lower the orbital gateway that once kept the body in remote isolation. Once that happens, the Sun begins to draw the object through a very long descent. The body is still far away, still frozen, still silent, but it now belongs to a different history. It is no longer merely stored material. It is material in transit. That transition carries a severe stillness. The object does not know that its role has changed, and nothing about its appearance may reflect the new path. It remains dark. It continues to receive very little sunlight. It does not grow a tail or a surrounding cloud of gas. In physical terms, it may look almost exactly as it does before the disturbance. What changes is the future written into its orbit. This is part of what makes the first inward fall so unsettling. One of the most important transitions in the life of a cometary body can occur with no visible drama at all. The timescale remains vast even after the fall begins. A body released from deep storage does not rush inward in any human sense. It may take hundreds of thousands or millions of years to move from the outer Oort region toward distances where astronomy would later have a chance to detect it. Near the farthest part of its orbit, motion is slow. The Sun still governs the path, but the orbit is so large that the body lingers in deep space for an extraordinary share of its journey. The inward fall is real from the beginning, yet it remains stretched across time. This slow descent is governed by orbital mechanics rather than by friction or propulsion. The body is not flying through a resisting medium that breaks or heats it. Space is too thin for that to matter. Instead, gravity alone shapes the path. As the body moves inward, it gradually converts orbital potential into greater speed. Potential here refers to the stored effect of being high in the Sun's gravitational field. Far away, the body moves slowly. As it descends, it accelerates. The increase is steady and lawful, built into the shape of the orbit itself. The first inward fall is therefore not a random plunge. It is a precise consequence of a changed path. Even so, the path remains fragile in its early stages. The object has not yet become part of the familiar solar system. It is still in the remote domain where outside influences matter. Additional weak disturbances may continue to affect it while it remains far out. Some bodies may be nudged further inward. Others may have their paths altered again before they travel much closer to the Sun. A few may be sent back into deeper storage or removed from the solar system altogether. The start of inward motion is not always a guaranteed delivery. It is the opening of a route, not the certainty of arrival. This uncertainty is scientifically important. Not every disturbed Oort Cloud body becomes a visible long-period comet in the inner system. The reservoir is vast, the pathways are varied, and the external influences that reshape the distant cloud do not act with simple uniformity. Observations indicate that galactic tides and stellar passages can inject bodies inward from the cloud. It remains uncertain in detail how often particular regions contribute, how much the rate varies across long spans of time, and how many potential visitors are lost before they ever approach the Sun closely enough to become visible. The first inward fall is a real process, but it is not a guaranteed outcome for every disturbed body. There is a quiet terror in that hidden significance. The cloud may contain countless bodies that appear inert and irrelevant because they remain so far away. Yet any one of them can, under the right gravitational circumstances, stop being a passive resident of the distant reservoir and begin a descent that will eventually bring it toward the Sun. The change does not require violence. It does not require collision. It does not require any event that would look dramatic if viewed at one moment in time. It requires only the patient work of gravity across distance. The first inward fall therefore marks a subtle crossing from one state of existence to another. Before it, the body is chiefly part of the Oort Cloud as storage. After it begins, the body is still part of that cloud, but also part of a migratory stream moving out of remote isolation. The object remains ancient, cold, and almost undetectable. Its surface stays quiet. Its appearance stays unchanged. Only the orbit tells the truth. Deep in the outer darkness, long before any tail forms and long before any telescope notices, the body has already ceased to be only a hidden remnant. It has become an inward-falling messenger of the farthest solar system, set on a course that begins in silence, across the empty outer solar system. The inward-falling body remains almost exactly what it has long been in the Oort Cloud. It is still frozen, still dark, still inactive in any obvious sense. The great difference is location rather than appearance. It is no longer only part of the deep surrounding reservoir. It is now moving through the broad remote reaches between that reservoir and the more familiar planetary system. This is an immense corridor of distance, one that contains little to mark progress and almost nothing to announce the body's approach. The journey continues, but the traveller remains largely hidden. The outer solar system at this stage does not resemble the region of bright planets, often shown in simple diagrams. It is not a place where a comet immediately becomes visible once it leaves the Oort Cloud. Most of the route inward lies through darkness so complete and through distances so vast that even a substantial change in position means little in visual terms. The Sun is brighter than it is in the cloud's deepest frontier, but still weak compared with the sunlight known near Earth. The body receives more energy than before, yet not enough to transform its surface into an active comet. It remains a nucleus in storage-like condition, only now in motion across a long empty passage. That passage is empty in a careful scientific sense. It is not truly vacant. Scattered dust, faint radiation, magnetic fields, and tenuous gas are still present. Yet none of these gives the region a lived structure. There are no landscapes, no nearby reference points, and no dense population of visible objects surrounding the inward-moving body. The distances between meaningful landmarks remain enormous. The result is a journey that is dynamically real but visually mute. The body advances through a zone where there is almost nothing to reveal that it is there. This is one reason detection remains so difficult. Telescopes rely on light, and the inward falling nucleus offers very little. It does not shine by its own power. It only reflects sunlight, and at these distances that reflected light is weak. The nucleus itself may be only a few kilometers across, with a dark surface that reflects poorly. Even a larger body remains hard to detect when placed so far from the Sun and Earth. The surrounding space adds no strong contrast, because the object is not wrapped in a bright cloud of gas or dust. It is simply a cold, dark body moving against a field of stars. Modern surveys can discover distant objects far beyond the orbits of the known planets, but the challenge remains severe. A dormant comet nucleus from the Oort Cloud can pass through enormous stretches of the outer solar system without attracting notice. Its brightness may stay below detection limits for a long time. Its motion across the sky may be slow enough, and its reflected light faint enough, that it blends into the background. This means that a body can spend much of its inward journey effectively unseen, even while it is already committed to a path carrying it closer to the Sun. The physics of the body changes only gradually here. Sunlight slowly strengthens with decreasing distance, but not in a way that immediately awakens the surface. The ices remain mostly stable. The volatile compounds that later begin to escape as gas still stay frozen, or nearly so. There may be subtle local changes in the uppermost material, depending on composition, surface texture, and exact distance. But in general, the body remains inactive through this long outer approach. It does not yet build a coma, the temporary atmosphere of gas and dust that surrounds an active cometary nucleus. Without that coma, it remains much smaller and much dimmer to distant observers. Its motion, however, is not unchanged. As the body descends farther into the Sun's gravitational field, its speed increases. This increase is steady and lawful, arising from the shape of the orbit. Near the outermost parts of the path, motion is slow and almost motionless by human instinct. Farther inward, the descent becomes less languid. Even so, the scale of the outer solar system keeps the process from feeling rapid. The body may be accelerating, but it is accelerating across a gulf so large that the entire scene still appears calm. This combination of growing motion and continued invisibility gives the outer passage its quiet tension. The body is no longer a fixed remnant in deep storage. It is becoming an active participant in the solar system's internal traffic. Yet it has not acquired the visible features that would reveal that role. It is a moving threat or a moving scientific opportunity long before it is a moving spectacle. The empty outer system therefore acts as a concealment zone. It allows the object to travel inward for immense distances while still remaining, in practical terms, hidden. The region also tests the limits of astronomical knowledge. Observers know that the Oort Cloud supplies long-period comets. They know that these bodies must cross the outer solar system on the way inward. Yet many individual journeys through this zone are never seen directly from start to finish. Instead, the existence of the passage is reconstructed from later observation and from orbital calculations. A comet appears much closer to the Sun, and its earlier path is worked backward. The long unseen approach through the outer emptiness is then understood through mathematics, rather than witnessed scene by scene. The body crosses a region that is scientifically expected but often observationally silent. This silence helps explain why the Oort Cloud can feel more threatening than it first appears. Its bodies do not usually arrive with generous warning. They spend much of their inward travel in a state that is both real and difficult to observe. The empty outer solar system hides them by scale, by darkness, and by inactivity. It is not a barrier in the usual sense. It is a long, quiet corridor in which a body can move closer while remaining almost entirely unknown. Across this corridor, the nucleus continues its descent without fanfare. It stays frozen. It stays dark. It drifts through a region where distance itself acts like camouflage. The sun grows gradually stronger, the orbit steadily tighter, and the velocity slowly greater, yet the body still preserves the outward appearance of dormancy. This long approach through the empty outer solar system is therefore one of the most deceptive parts of the comet's history. It is a stage of undeniable movement concealed inside apparent stillness, a crossing where a distant remnant advances toward the inner realm while remaining, for much of the journey, almost impossible to see. When an inward falling body from the Oort Cloud reaches the region of the giant planets, the quiet logic of the outer journey changes. Distance still dominates the scale, and the sun still governs the broad orbit, but another layer of control now comes into play. The great planets occupy this zone as massive gravitational authorities, and their presence turns a long, smooth descent into a passage filled with possible redirection. An incoming comet does not simply continue inward as though nothing new is there. It enters a gate made of moving worlds, and each of those worlds has the power to alter its fate. This is especially true of Jupiter. Among the planets, Jupiter carries the greatest mass, and with that mass comes the strongest local gravitational reach. A comet entering the giant planet region may never strike Jupiter, never pass close enough to see the planet as anything but a distant world, and yet still feel the consequences of Jupiter's presence through the shape of the orbit. If the path brings the comet near enough, Jupiter can bend that path sharply. It can shorten the orbit, stretch it, tilt it, or send the body away on a new route that differs greatly from the one it followed in from the Oort Cloud. This effect comes from a gravitational encounter. An encounter does not require impact. It means the comet passes through a region where the planet's gravity becomes an important local force in addition to the pull of the sun. During such a passage, the comet and the planet are both moving. The result is not a simple tug toward a fixed point. It is a transfer of orbital energy and direction within the larger solar system. The comet may leave the encounter traveling faster relative to the sun, or slower, depending on the geometry of the passage. Its future then changes accordingly. For a comet arriving from the Oort Cloud, this makes the giant planet region a sorting zone. Some comets pass through without a particularly close encounter and continue along paths not greatly changed. Others come near a planet and are redirected into new orbits that keep them bound to the sun but alter the scale of their return. A very long-period comet may be transformed into an object with a shorter and more frequent orbit. In this case, the giant planet acts almost like a captor, not by stopping the comet, but by reducing the size of its path and making it a more regular member of the solar system's moving population. Jupiter is especially important in this respect because it can create what astronomers often call Jupiter family comets over long time scales. Though the exact transition from a distant long-period orbit to a shorter Jupiter-controlled path may involve repeated encounters and gradual reshaping rather than a single event, the central principle remains clear. Jupiter can take a body that arrives from the farthest solar system and make it part of a much tighter orbital pattern. A comet that once spent millions of years in remote darkness may, after planetary encounters, return much more often. The giant planet gate can therefore convert rare visitors into recurring ones. Yet capture is only one outcome. The same gravitational power can also expel. If an encounter gives the comet enough additional energy relative to the Sun, the orbit may cease to be a closed ellipse and become an open path. In plain terms, the comet is then no longer bound to the solar system. It is flung outward into interstellar space. This does not require violence in the human sense. The body simply passes through the gravitational field of a giant planet in such a way that it leaves with escape energy. A remnant preserved since the early solar system can thus be removed from the Sun's domain by one critical passage through the planetary gate. Saturn also plays a significant role, though less strongly than Jupiter because it is less massive. Uranus and Neptune matter as well, especially in the earlier shaping of distant icy bodies and in certain orbital pathways through the outer system. Together, the giant planets form a layered set of gravitational barriers and opportunities. A comet may first pass through Neptune's distant zone, then face possible influence from Uranus, then Saturn, then Jupiter. Each stage can modify the path. A body that survives one encounter remains exposed to another. The gate is therefore not a single doorway. It is a sequence of moving gravitational tests. These interactions do not merely change whether a comet stays or leaves. They also change how the body moves through space. The tilt of the orbit may shift. The closest point to the Sun may move inward or outward. The farthest point may be reduced or extended. The orbital period may shrink from immense spans to much shorter ones, or be lengthened again by later encounters. In some cases, the result is temporary stability. In others, the path becomes chaotic in the mathematical sense, meaning that small differences in one encounter can lead to very different futures after repeated passes. The giant planet region is therefore one of the least forgiving parts of the journey. It is where long quiet storage gives way to dynamic uncertainty. There is also a scale problem that deepens the unease. Jupiter and the other giant planets do not need to patrol every direction. Their gravitational domains are enough. A comet entering the planetary region is no longer moving through emptiness alone. It is crossing a space filled with massive bodies that can redirect it without warning. The farther outer passage hides the comet through distance. The giant planet gate tests it through gravity. Here, the inward falling remnant becomes subject to concentrated decision points written into orbital geometry. This is why the region feels like a true gate rather than merely another stretch of space. A gate is a place where passage changes status. Before entering it, the comet is mainly a distant migrant descending from the Oort Cloud. Within it, the comet becomes something judged by encounters. The giant planets decide, through gravity alone, whether the body continues inward on a similar path, settles into a new sun-bound orbit, or is expelled from the solar system altogether. The comet carries its ancient material unchanged in origin, but its future is no longer governed by distance alone. It is now governed by close relation to moving giants. The terrifying part is the calm efficiency of the process. No guardian stands at the threshold. No visible barrier marks the border. The gate exists because mass exists. The giant planets simply follow their own orbits, and any incoming comet must cross a region where their gravity matters. Some pass through altered only a little. Some are claimed into shorter paths. Some are cast away forever. The Oort Cloud sends its frozen bodies inward across immense ages, but the giant planet zone determines which of those bodies remain visitors, which become residents of a different kind, and which disappear into the dark beyond the sun's reach. Near the sun, the ancient body from the Oort Cloud stops resembling a dormant archive and begins to reveal the unstable nature it has carried all along. This change does not happen because the comet enters an atmosphere or collides with surrounding matter. It happens because sunlight, after remaining weak for almost the whole inward journey, finally becomes strong enough to alter the surface directly. Energy that once passes over the nucleus with little consequence now begins to penetrate the upper layers and warm frozen material. The body awakens not by gaining life, but by losing itself. A comet nucleus is usually small, dark, and irregular in shape. It does not gleam like polished ice. Its surface often reflects very little sunlight, partly because it contains dust, carbon-rich material, and space-weathered crust rather than clean bright frost. This darkness matters. A darker surface absorbs more of the incoming sunlight, and as the comet moves closer to the sun, absorbed heat begins to accumulate in the near-surface layers. The change is still gradual, but it is decisive. Volatile substances that remain stable in the deep outer system can no longer remain fixed in solid form. They begin to sublimate, meaning they pass directly from solid to gas. Sublimation is the central process of the comet's awakening. In the near vacuum of space, many frozen substances do not melt into liquid first. Instead, they escape from the solid state into gas when warmed sufficiently. Different ices respond at different distances from the sun, depending on their composition and the physical structure of the nucleus. The more volatile compounds can begin this transformation earlier, while water ice often becomes especially important closer in. As gas forms beneath or within the upper surface, pressure builds in pores, cracks, and weak layers. Eventually the gas escapes outward, dragging dust grains with it. This escaping material creates the coma. The coma is the broad temporary cloud of gas and dust that surrounds the nucleus once activity begins. It is not an atmosphere in the planetary sense, because the comet's gravity is far too weak to hold the gas permanently. Instead, it is a constantly renewed envelope, produced by ongoing sublimation and lost steadily to space. The coma can grow to enormous size compared with the tiny nucleus at its center. A body only a few kilometers across can produce a surrounding cloud far larger than planets, not because the comet is massive, but because gas and dust disperse outward into the vacuum with little restraint. The coma is one reason comets become visible from great distances. Before awakening, the nucleus is small and dark. After awakening, the surrounding cloud presents a much larger light-scattering surface to sunlight. Dust in the coma reflects and scatters visible light. Gas in the coma can also glow through interaction with solar radiation, though dust often dominates what is seen in ordinary views. The comet therefore brightens not because the solid body itself becomes brilliant, but because the sun illuminates the expanding material the body is shedding. The ancient remnant first becomes conspicuous at the very moment it begins to erode. Tails form from this same outflow, but they are shaped by different influences once the gas and dust have left the nucleus. Dust released from the coma tends to be pushed into a broad curved tail by sunlight itself. Tiny particles feel radiation pressure, a gentle outward force carried by light. Gas behaves differently. Charged particles and ionized gas interact strongly with the solar wind. The continuous flow of particles moving outward from the sun. This can produce a straighter ion tail that points more directly away from the sun. A comet may therefore display more than one tail at once, each created from the same loss of material but shaped by different solar forces. The important fact is that the tail does not trail behind the comet, like smoke behind a moving vehicle. It points according to the direction of sunlight and the solar wind. This makes the comet's appearance both elegant and deceptive. What seems like decoration is actually evidence of destruction. The bright tail records the continuous escape of material that once remains locked in the nucleus. Every visible plume and sweeping extension testifies to instability at the surface. The more active the comet becomes, the more clearly it displays its own gradual loss. That loss is rarely smooth. A comet nucleus is not usually a uniform ball of identical ice. It is a mixed body with uneven composition, layered deposits, surface crusts, cracks, and shaded regions. As sunlight warms different areas under changing geometry, activity can become patchy. Gas may burst more strongly from certain vents or weak spots. Dust jets can emerge from localized regions where the surface opens. Some slopes remain relatively quiet while others release material vigorously. Rotation adds further complexity, because different parts of the surface take turns facing the sun. The awakening is therefore not simply a global warming of the whole nucleus. It is a rotating and uneven pattern of exposure, escape, and collapse. This process can alter the body in visible and invisible ways. Surface layers may crack or slump as buried volatiles escape. Dust may settle back onto quieter regions and build an insulating crust. Active vents may open, weaken, or shut down. The nucleus may lose mass steadily, sometimes with sudden outbursts when trapped gas breaks through a sealed layer. Each passage near the sun can therefore reshape the comet. Some comets fragment under thermal stress or internal weakness, splitting into multiple pieces. Others survive repeated passages but emerge changed, their surfaces darker, more depleted, and less active than before. The awakening near the sun is never just a display. It is a period of physical transformation. The terrifying part of this awakening lies in the scale of the contrast. A body preserved in cold silence for immense spans of time can become visibly active within a comparatively short segment of its orbit. Material older than Earth's surface history begins to stream away into space. Frozen compounds that remain trapped since the early solar system suddenly join the coma and tail, where telescopes and spacecraft can study them. What has been hidden in the Oort Cloud for ages becomes briefly readable only by being lost. This is why the comet's brightness carries such a severe scientific meaning. The sun does not merely illuminate the ancient remnant, it excavates it. The coma and tails reveal composition, dust content, and activity, but they do so by stripping the nucleus layer by layer. The spectacular appearance that draws attention in the inner solar system is inseparable from erosion. The comet wakes by shedding its stored past into surrounding space. Near the sun, then, the Oort Cloud body finally becomes what human observers recognize as a comet. Gas escapes, dust rises, the coma swells, tails extend outward under light and solar wind. Jets flare from uneven terrain. The once hidden nucleus brightens only through ongoing loss. Its most visible state is also its most vulnerable state. After ages of dark preservation, the body announces itself by dissolving at the edges, turning sunlight into motion, and turning deep frozen storage into a brief and luminous unravelling around the sun. In the terrestrial planet region, the long inward history of an Oort Cloud body becomes dangerous in a new way. Far from the sun, the object is mainly a problem of distance, invisibility, and time. Near the giant planets, it becomes a problem of redirection. Closer still, where Mercury, Venus, Earth, and Mars occupy their compact inner orbits, it becomes a problem of speed and crossing geometry. The same ancient body that spends most of its existence in deep cold now passes through the densest inhabited part of the solar system's inner architecture. It does not belong there in any settled sense. It passes through it on a steep, swift, and often temporary route. This region is small when compared with the breadth of the Oort Cloud, yet it is crowded in dynamical meaning. The rocky planets move quickly around the Sun on comparatively tight paths. Their orbital planes remain broadly aligned with the original flatness of the solar system. A long-period comet arriving from the Oort Cloud often does not share that alignment. Its orbit may cut across the planetary region at a sharp angle. It may descend from far above the usual plane or rise from far below it. It may pass through the inner system only once in any humanly relevant span of time. The result is that the terrestrial planet region receives visitors whose paths are not shaped by long residence there, but by remote origin and enormous orbital scale. Speed is the first reason this becomes threatening. By the time a comet from the Oort Cloud reaches the inner solar system, it has fallen a great distance through the Sun's gravitational field. That fall steadily increases its velocity. Near the terrestrial planets, the comet can be moving much faster than many ordinary asteroids that spend long periods in the inner system. If its orbit is also highly inclined or retrograde, meaning it moves around the Sun in the opposite direction from the planets, the relative speed during any close approach can become especially large. Relative speed matters because it determines how violent an encounter would be if impact occurs. Energy increases very rapidly with speed. A modest change in velocity can produce a much greater change in destructive effect. This does not mean every long-period comet is headed toward collision. Most are not. The inner solar system remains mostly empty even here, and the planets themselves occupy only tiny fractions of the available space. But when an Oort Cloud comet does enter the terrestrial region, the hazard it represents is shaped by a combination of factors that differ from the slower and more familiar picture of a stable, inner solar system body. The object may arrive on a path that crosses planetary orbits rather than resembling them. It may be active, which can complicate measurements because outgassing can apply small additional forces to the nucleus. It may also be a fragile body, prone to shedding dust, jets, or fragments as sunlight intensifies. Fragmentation adds another layer of unease. A nucleus warmed strongly near the Sun can crack, split, or lose pieces. If that happens while the comet is moving through the terrestrial planet region, the hazard is no longer tied only to a single compact body. Multiple fragments may continue on related paths, each one carrying its own mass and momentum. Dust and small debris also spread along nearby portions of the orbit. Most such material is harmless at planetary scale, yet the physical instability of the nucleus means that the exact structure of the threat can change while the comet is already in the region where planetary crossings matter most. The body that enters is not always identical to the body that leaves. The geometry of the crossing also matters. Planets follow repeated nearly circular paths, while a long-period comet often follows an elongated path that slices through the system. It may spend only a short time near the Sun and the inner planets before racing outward again. This means the interval during which the comet can come near a terrestrial world is brief compared with its total orbital period. But that brief interval is also the moment of greatest consequence. The danger concentrates where the orbits intersect in both place and time. A crossing path is harmless if the planet is elsewhere. It becomes serious if planet and comet reach the same zone together. Earth occupies one of these crossing possibilities. It moves on its ordinary yearly path, while the comet arrives on a trajectory shaped by deep time. If their positions coincide closely enough, the result can be severe. The nucleus of a long-period comet may be smaller than a planet by many orders of magnitude, yet the energy released by impact can be immense because of high velocity. Even an object that is not especially large in planetary terms can carry extraordinary kinetic energy by the time it reaches Earth's orbital distance. A larger nucleus or fragment would be more consequential still. The threat is therefore not only a matter of size, it is a matter of speed joined to mass. Another reason the terrestrial planet region feels especially exposed is that long-period comets can remain difficult to characterize until relatively late in their approach. A dormant or weakly active body can stay faint for much of its inward journey. It becomes easier to detect and study only after sunlight drives more activity, or after it moves close enough for surveys to follow it more effectively. By that stage, the object may already be descending rapidly through the inner solar system. The late brightening that makes the comet visible is the same process that reduces the margin of time in which its path can be refined. The danger is therefore linked not just to where the comet travels, but to when it fully reveals itself. Outgassing can complicate this further. As gas escapes from the warming nucleus, the flow can act like a weak natural thrust. Usually this effect is small compared with the overall orbit, but for precise prediction it matters. A comet is not always a passive ball following gravity alone once it becomes active. Jets can alter rotation, shift the surface, and produce slight changes in motion. Over long intervals, these small effects may accumulate enough to complicate the exact tracing of the path through the terrestrial region. The object is ancient, but its behavior near the Sun can become changeable. This makes the Earth crossing zone quietly severe. The terrestrial planet region is where long-period comets combine their greatest visibility with some of their greatest danger. They arrive at high speed after falling inward from the remote cloud. They may cut sharply across the planetary plane. They may brighten late, fragment, or alter activity as they warm. Their encounters with the inner planets are brief in duration but large in consequence. Nothing about the region looks dramatic from a distance. The planets continue their regular motion. The comet follows its own lawful descent. Yet where those two patterns meet, the inner solar system becomes a crossing zone in the strictest sense. A place where an ancient remnant from the farthest sunbound dark can move through the small inhabited architecture of the rocky planets with very little room for error. The human warning line begins not at the edge of the Oort Cloud, nor in the empty outer passage, nor even at the gate of the giant planets. It begins when the inward falling body becomes visible enough, bright enough, or close enough for instruments on or near Earth to separate it from the background of the sky and recognize it as an object on the move. This line is not a physical border in space, it is an observational border. On one side of it, the comet exists only as an unseen traveller. On the other side, it enters human awareness. The crossing can happen late. That lateness is one of the most unsettling facts about long-period comets from the Oort Cloud. Their journeys begin in remote darkness and continue across immense distances in near invisibility. For most of that history, the body is too faint, too small, or too inactive to be easily found. Even a modern sky survey, scanning large areas of the heavens with far greater speed and sensitivity than earlier generations can achieve, must still work against distance, low brightness, changing weather, limited geometry, and the simple vastness of the sky. A comet can therefore be real, inbound, and significant long before it becomes part of human knowledge. When discovery finally happens, it usually happens through light. The nucleus may still be too small to reveal much on its own, but once activity begins and a coma develops, the object brightens and spreads its reflected sunlight across a larger visible form. Survey telescopes record a moving patch of light. Repeated images show that the patch shifts against the fixed stars. Software and observers compare positions, link detections, and determine that the object is not an ordinary star or galaxy. It is a body inside the solar system, arriving from far beyond the planets. Only then does the long-hidden journey become an observed event. This first detection is rarely the same as full understanding. A newly discovered comet often arrives with uncertainty attached to it. Its path has to be measured through repeated observations across time. Each new image extends the observed arc, this segment of the orbit actually recorded by human instruments. At first, that arc may be short. With only a short arc, the orbit remains less certain. The object is known to be moving, and its general direction may be clear, but the exact future path, brightness, evolution, and physical character may still be poorly constrained. The warning line is therefore not only the moment of discovery, it is the beginning of a race between the comet's inward motion and human refinement of knowledge. This race depends on astronomy of a very practical kind. More measurements improve the orbit. More nights of observation reduce uncertainty. Larger telescopes may examine the coma, estimate brightness, and search for signs of tail development or fragmentation. Spectroscopy, the splitting of light into its component colors, can reveal gases escaping from the nucleus and help characterize composition. Imaging over time may show jets, asymmetry, or changes in activity. Radar is usually limited by distance and brightness. So much of the early understanding depends on optical and infrared observations. Each method adds information, yet all of it begins only after the object crosses the warning line into detectability. The difficulty is that long-period comets often do not grant a generous interval between first recognition and closest approach to the Sun and inner planets. Their high speed in the inner solar system compresses the remaining timeline. A body that spends millions of years in remote storage can move from initial visibility to inner passage in a comparatively short span. This does not mean that every such comet appears with almost no notice. Some are found earlier than others, some brighten at more favourable distances, some approach on geometries that aid discovery, but the basic problem remains. The most distant part of the journey hides the object. The most important part of the journey unfolds after it is finally seen. Brightness itself can mislead. A comet may look impressive in the sky because the coma and dust reflect abundant sunlight. Yet the nucleus at the centre may still be difficult to measure precisely. The visible cloud can make the object easier to detect, while complicating efforts to determine the exact size and condition of the solid body. A bright comet is therefore not automatically a well-understood comet. It may be visually obvious and physically uncertain at the same time. Outgassing can further complicate the picture by applying small non-gravitational forces that subtly alter the path. These forces are often weak, but when predictions must be precise, weak forces matter. Fragmentation is another reason the warning line is uneasy rather than reassuring. A comet may be discovered as a single object and later begin to split, shed mass, or change activity as it approaches the Sun. This can alter brightness, modify the appearance of the coma, and in some cases complicate the tracing of the nucleus or larger surviving fragment. Human awareness begins at discovery, but the object itself continues to evolve. Knowing that something is coming does not instantly mean knowing exactly what it will become before it passes through the inner solar system. The human warning line also reveals a deeper limitation. Humanity does not stand outside the solar system watching all of it at once. Observation happens from within the system, from a moving planet with an atmosphere, daylight, weather, seasonal geometry, and only partial access to the whole sky at any given moment. Space telescopes expand that reach, and coordinated surveys greatly improve coverage. But the act of discovery still comes from a local interior perspective. A comet from the Oort Cloud approaches from a three-dimensional outer domain. Human beings search from one small moving world inside that domain. The asymmetry is profound. The object can arrive from almost anywhere. The watchers remain in one place. This is why the warning line feels less like a secure defense than a threshold of late knowledge. It marks the moment when the unknown becomes measurable, but not the moment when the danger begins. The danger, if danger there is, begins much earlier in orbital terms, long before any eye or detector records the object. Discovery simply brings that hidden history into awareness. It converts a silent traveller into a tracked one. It allows prediction, study, and where relevant, planetary defense analysis. Yet it never fully removes the fact that human knowledge starts after the journey has long been underway. That is the final inward truth of the Oort Cloud's visitors. They are not terrifying only because they come from far away. They are terrifying because the line between ignorance and recognition lies comparatively near the end of their long descent. Humanity sees them only after distance, darkness, and inactivity have done their work. By the time the comet enters the warning line, the ancient body has already crossed most of its hidden path. Instruments awaken to it. Calculations close around it. Telescopes study its gases, dust, and motion. The object becomes known, but it becomes known late. The human warning line is therefore not a place of comfort. It is a place where understanding finally begins after the deep outer history has already committed the visitor to arrival. The Oort Cloud remains distant, dark, and almost entirely unseen, yet it gives the solar system one of its largest and most unsettling dimensions. It begins as a hidden outer reservoir, shaped by exile, deep time, and the slow influence of the galaxy. It keeps ancient bodies in cold storage so far from the sun that ordinary images of the solar system no longer suffice. It surrounds the familiar planetary region not with a bright border, but with a vast as nearly invisible archive of early matter. Its terror does not lie in constant violence. It lies in scale, exposure, and delay. The cloud is sparse, yet immense. It is quiet, yet never fully secure. Passing stars, galactic tides, and the slow balance of gravity continue to work upon it across ages too long for instinct to hold. From that distant silence, some bodies begin the long inward fall. They cross the empty outer system unseen, past the giant planets under judgment of gravity, and only near the sun reveal themselves by beginning to come apart. What reaches the inner solar system is therefore not simply a comet in the ordinary sense. It is a survivor from the solar system's earliest disorder, preserved in darkness and awakened only through erosion. Its brightness comes from loss. Its visibility comes late. By the time human beings detect it, most of its journey is already complete. Knowledge begins only after the ancient body has crossed the greater part of its hidden path. This gives the Oort Cloud its lasting weight. It is not merely a source of comets. It is the outer memory of the solar system, stored beyond direct sight and carried through the Milky Way with a boundary that never fully closes. It remains a sphere of frozen remnants, quiet in appearance, uncertain in detail, and immense beyond ordinary thought. Around the bright inner worlds, that dark reservoir continues to wait, keeping its distance, keeping its silence, and sending inward from time to time a reminder of how large the sun's true domain still is,